think let's go like you tell me when.
Start.
Yeah. So welcome everybody. This is a series of public talks on recent discoveries which we started at the Indian Institute of Astrophysics. We'll be covering important announcements, discoveries in the field of astronomy hereafter. Those are which are of public interest, and I think there's no greater topic of public interest than black holes and the Big Bang and dark energy and dark matter. So I think we're very happy to have both these announcements this year, one in March and one in April. And therefore we have double billing today. The first we're going to have a talk by Subinoy on the results from the DESI, the Dark Energy Spectroscopic Instrument, and followed by a talk by Sanved on the polarization images released by the Event Horizon Telescope of the black hole in the center of our own galaxy. So the way we'll do this is that we'll first have a talk by Subinoy, followed by maybe a couple of questions, followed by a talk by Sanved Kolekar, both of which will be around half an hour, followed by a couple of questions for him, and then we'll put both them here, and then it's a free for all. You can do what you want to. Yeah. So now we are joined by our colleagues on Zoom as well as YouTube. So welcome to those online as well, and we'll take questions from YouTube, Zoom, and people in the audience as we move along. So to start with, the first talk will be by Subinoy Das. He's a faculty here at the Indian Institute of Astrophysics, and he did his master's in IIT Kanpur and then MPhil in physics from Columbia University in the US. He did his PhD in particle physics and cosmology from New York University, and then he did a couple of postdoctoral stints at UBC Canada and RWTH Germany. He's been in IIA since 2013 as a faculty member, and his main research areas involve probing fundamental nature of dark matter and dark energy, as well as cosmic neutrinos and their implications on the universe. So today is going to talk about the Dark Energy Spectroscopic Instrument results, DESI, and therefore Subinoy, please.
Yeah.
You already mic'd up? Yeah.
Thank you, Neeraj and Vikram, the IIA Scope team, for arranging these beautiful topics and the recent discoveries. So, as I don't gauge the audience, so I kept it some videos also for people who has no idea what dark energy is, and also little bit mathematics, people who has some idea, so that everybody can take home something. Okay, so before I go into the exact discovery and the topic of dark energy, so this is the brief story of our own universe, and just to let you know that something called Big Bang happened and a rapid expansion, much faster than the speed of light at the beginning of time, around 14 billion years back, and then there was a rapid expansion, and then we ended up in hot Big Bang. So there is a confusion. People think hot Big Bang means this explosion. Actually, it is not. A hot Big Bang means we don't know what happened at the time t equals to 0. It's a singularity. But we know that we ended up in a very hot plasma universe. And then that expanded and it cooled down. And after 200 million years, the first galaxy formed. And somehow the gravity could win over the expansion of the universe, because expansion wants to take away things and gravity wants to bring things together, and you need to bring things together to form stars, galaxies, and life. And that was happening. And then around 9 or 10 billion years later, from this dark part, we kept it dark because the dark energy kicked in. And we don't see dark energy because it's an energy form which does not interact anything other than gravity. So just by looking at the expansion rate, which I'll talk to you, explain you later, we could find out, the Nobel Prize came in 1998, that there is some mysterious energy, again rapidly expanding the universe, accelerating. It is as if you started the car with acceleration, huge acceleration, that is after Big Bang, much faster than the present dark energy. Then it cooled down, slowed down, and again at 8 to 9 billion years later, as if the universe has again pressed the acceleration and we are going away from each other. Now, why it is so important? Why it is so important to know the value of dark energy, its property? Because it is connected to our own existence. If dark energy could take over a little bit earlier, then no galaxy could form. So somehow in this zone, dark energy was subdominant. It was just waiting. And today I'll tell you, this tuning of value of dark energy has to be so much fine-tuned, and that's called fine-tuning problem of dark energy, that it takes over the universe at around 10 billion years. So that before the galaxy can form and life can come and you can watch the talk today. Okay? So that's the idea of our brief history of universe. So now, Einstein didn't know. If you look at the night sky, you will not see that it is expanding. In fact, Einstein believed that it's an eternal universe, static universe. But from his own discovery, from general theory of relativity, he found an equation. I mean, you can, in our graduate study, we all do this equation. This is like the velocity of the space, A dot. A is the scale factor. It can tell you how fast space is expanding. So if A dot is 0, that means there is no velocity of the space. So Einstein himself found that if any energy is there in the universe, and we know universe is filled with energy, there is matter, there is dark matter, there is photons, there is so much, then you cannot make universe static from his own equation. But he believed in static universe. So he himself came up with this idea called cosmological constant. It's a vacuum energy which is present in the universe from quantum field theory. I'll not go into that. Just a basic idea about it, that in classical physics, you can make a particle flow and make it stop, kinetic energy 0 and potential energy 0. But in quantum mechanics, even the 0 point energy, you cannot make it 0. It is non-zero. So, a whole universe is basically, once you know more advanced quantum mechanics, is basically infinite number of like classical harmonic oscillator in the space, and each point has a non-zero energy. So as a whole, the vacuum, the emptiness, means if you take away everything from this space, matters, everything, what is nothing, actually not nothing in quantum field theory, you will get a non-zero energy, and that energy is called cosmological constant or vacuum energy. So he put it, same term, in the left-hand side to balance this row to get a static universe. And later, he called his biggest blunder when Hubble discovered that universe is indeed expanding. And where it is expanding into, that is a question for you. It is not expanding, the space does not have a boundary. So it is not that the space is expanding into another space, no. So today I will not go into that, because the space is already infinity, but still you see that everything is going away from each other. So space is actually expanding into itself. Okay, so any wavelength, that's why it gets stretched. That is called cosmological redshift. Because if you measure today, and if you measure the same wavelength 5 billion years later, you'll see it is stretched. A ruler will be stretched because space is expanding. Okay, so now, how fast is space is expanding? Can it accelerate like a car? That's I told you. Yes, it can. Can it put a brake? Till now, the last 20 years, we thought it cannot. Because if cosmological constant is dark energy, what that the Nobel Prize got the existence of dark energy, and cosmological constant is kind of the only possible candidate of dark energy, we call it lambda, and the cold dark matter we call it CDM. And the lambda CDM universe is kind of like the best fit universe from any lot of experiment. And for the last 20 years, we are almost believing that it's the lambda and the vacuum energy will continue to expand the universe and accelerate. So it cannot break. But the DESI result, first time ever, is telling maybe universe can decay the dark energy away or can put the brake again. So our fate will be completely different. That is the talk today. What will be the fate of the universe if there is no brake, and what will be the fate of the universe if there is a brake. So that's I already told. The expansion of the universe, suppose this balloon is expanding. If you are in the center, if you have access to the 3 dimension, then you will think that there is a center of the expansion. But suppose you are an observer or you are an alien, only you have access to the surface, then you will not know that where the expansion is happening from. There is no center. Because you will only see everything is going away from each other on the surface. So our situation is like that. there is no preferred center of the universe. So whatever we are experiencing here, if you go to another aliens or another galaxy, you will see that from there also they will see everything is going away. So they will feel they are the center. If you come here, you will feel you are the center. So wherever you go, you will be the center of the universe. Okay, there is no preferred center of the universe. And then once you have this idea of Big Bang, that universe is expanding, this guy, Lemaitre, I'm not going into the mathematics, it's called Friedman-Robertson-Walker metric. With some mathematics, he showed that there will be a singularity. That means the space-time loses its significance, meaning when you go to t equals to 0. You cannot even write a distance between 2 points. It's all collapses. So that's where the unknown is, but that is not called Big Bang. The Big Bang is after that you ended up in a hot. So this part is called singularity and we don't know what it is. Okay, how the time and space came into existence is a mystery, and still people are trying. Stephen Hawking tried, but there are a lot of controversies. No, it is still an open field of research. We don't know. So that's what the scale factor is. So suppose you have a sphere whose radius is r, and there is a particle here. You are measuring the distance as r. But as universe is expanding, even this particle is not moving from the center, but it feels like it is moving, and that is called the Hubble velocity. And that RT, the position, will be always a time-dependent factor, because if you measure today, A has a value, and if you come back after 1 million years and if you measure, you will see the particle is at rest, but they have moved away from the center. That's why you have to multiply this AT, that is called the scale factor, means how much your coordinate system is scaled bigger and bigger because of the expansion, and that is basically telling you how faster universe is moving. If you take derivative of it, a dot, dAdt, if you take a double dot, it tells acceleration. And in the beginning, AT equals to 0, A equals to 0, that is the Big Bang, and today A equals to 1. So, in fact, during Big Bang, we don't know what it was, but it has to be less than 10 to the power minus 70 or minus 80. That means the universe has become 10 to the power 70 or 60 times bigger compared to when it got created till now. Okay, so now there are different choices of expansion, if what will happen to the universe. So depending on the nature of the dark energy. So one is, universe is expanding and it can recollapse. That is called cyclic universe. Expansion, collapse, and it goes for eternity. Another is, it is expanding and then it becomes constant, so the size of a disk will not change anymore. Another one is the constant expansion, it will become bigger, bigger, bigger like that. And then this is the accelerated expansion, where it is accelerating. So these are the choices. And if it is cosmological constant, then this is the choice. It will continue to expand. So now little bit mathematics, those who want to do research or intensive in this direction. So how do we measure the expansion of the universe? So basically, you have to plot this thing, distance versus velocity. So Hubble said that the V is proportional to t. So further you go, the velocity will be higher. And if it is a constant velocity, V is h times d, a proportionality, then you will get this straight line. Okay. Now, suppose you know some technique through which you are plotting the Hubble velocity, the expansion velocity as a function of distance. You measure stars or supernova or further galaxies and you plot them. If you get this plot, that means you see for a given distance, you want to find the velocity, so that will come smaller compared to constant velocity. Because if you fix the distance, if you have a constant expansion, then you get a larger velocity. Which means at past you have a smaller velocity for the red curve, and today it is more velocity, so that's why it is accelerating. And for here, for the same distance, you have a larger velocity, because you have to draw a line here and then here, project. So that is decelerating universe. So if you have a plot, from there you can know how universe is expanding. Now it is easy to measure velocity from Doppler shift. Those who know Doppler shift, you know that the wavelength gets stretched if things, this is from special theory of relativity. So you can measure that, people can measure that by looking their velocity. And then measuring distance is very hard. And that's where the beautiful thing happened, that we want objects, sorry, it got cut here, with known brightness. Meaning, suppose I give you 100 power bulb, every one of them has same brightness. But if you put you here, then BDA complex, then Sony signal, and then Ajipura, you will see the same brightness is dimming, meaning you are putting it in a larger distance. Because their brightness is constant, that's why they are dimming, you can measure how far they are. Because it's a standard candle. Luckily, we got the same thing in cosmos, which is called which happened from the supernova burst. Doesn't matter where they burst, it's a special kind of supernova type 1A. Whenever they burst with the same brightness. So if you see them dimmer, that means they are farther. Because they are bursting in the same, because from their internal structure or chemical thing, they always burst in the same brightness. So that's why you can plot by looking at the supernova, and that's the job, that is called standard candle. But if they burst with different brightness, then you cannot say whether the dimmer or the fainting of the light is because of their intrinsic brightness or because they are further away. But as their brightness is constant, wherever they burst, if you see a dimmer or more fainter, that means they are further away. So you can plot the distance versus velocity, but from that is called type 1, the standard candle in cosmology. And that's what these guys did and got the Nobel Prize. They found the more points actually goes to the accelerating universe. It did not match. And nobody ever thought that universe could accelerate because nobody knew about dark energy. So if you just put normal photon matter, dark matter, it was actually decelerating universe. It was expanding but decelerating, as I showed you in the first that plot or the picture. So that's why, in fact, I met Adam Rees just 3 months back in Johns Hopkins. I went there, and on top of on the door, he has written a comment. He said, "The confusion I am facing now actually more dangerous than what I was facing when I was getting this." And what is the confusion he is facing? There is something called Hubble tension. The value of Hubble parameter, the expansion, does not match from the supernova data and the something other called cosmic microwave background data. That is even more intriguing, because if it is true, that means we don't understand our even lambda CDM, or many of the assumptions of the cosmology can go wrong. But I'll not go into that topic. So that is another big thing going on in the cosmology called Hubble tension. Different observations are not matching the value of the expansion rate. Anyway, so now again little bit of mathematics. Now, as you are accelerating, A double dot is positive. This comes from Einstein's equation, rho plus 3p, and there is a minus sign. So as A double dot is positive, you are getting positive acceleration. So rho plus 3p has to be less than 0. So p by rho, we call it W, equation of state, just a name, has to be less than minus 1/3. So dark energy is a fluid which has negative pressure. And cosmological constant, luckily, also satisfy that condition, because W or P by rho is -1 for cosmological constant. And that is the nature of vacuum energy. But the negative pressure is very interesting. We have never seen negative pressure in the history of physics, because anything, if you want to compress a gas, it resists you. That means it wants to push things apart, that is positive pressure. Here, many people again does a mistake that they think dark energy is a repelling fluid because it is making the universe going blow up. In fact, it's opposite. Dark energy is actually an attractive fluid. But when you put the attractive fluid in the universe, from the equation we know, it actually expands faster. So dark energy itself is not a repelling fluid. It's actually it's like a rubber sheet which wants to come closer. But when you put that in the universe, it's an all-pervading thing. The universe reacts to it and starts moving very fast. So that's from the Einstein's equation. I've been working on it for 20 years, but still I don't know how it happens. Mathematically, I know. But how it happens is very hard to know. That's why the GR part is not very easy to comprehend in the 5 senses. Newton's things you can still comprehend. Okay. So now this is what we have today, is our universe. Cake, cosmic cake. 68% is dark energy, 27% is dark matter. Dark matter means its pressure is 0, which is like a non-relativistic matter, like our body, the atoms, everything is belongs to 4% of the visible matter, and there are some 27% dark matter, which is like visible matter, but does not interact through any of the interaction. So we don't see them. So still that is a mystery. What is dark matter? And then all other stars, everything, the hydrogen, helium, visible intergalactic medium is only the remaining 4.5% of the universe. So 96% or 95% is unknown. It is for some people it is depressing. For us it is very impressive because we can do research and we can write paper. There are a lot of scope because there is unknown. Okay. So now the value of the cosmological constant. By measuring the expansion rate, because it's an equation, I showed you, you can actually measure how much rho or energy density of the cosmological dark energy is there, so that you get the acceleration you see from the supernova. And the value they got, and the value from vacuum energy, which I was telling, from quantum field theory or quantum mechanics, they don't match. And they don't match means this is the biggest mismatch in the history of physics. The observed value of dark energy is 10 to the power minus 120 times smaller, observed is 10 to the power minus 120 times smaller than theory. And this is what is a like 0.0000 120 zeros, 138 is the value of the dark energy. If you erase 1 or 2 zeros, it's like, because once you are doing physics and suddenly you get such a small number, you say that who ordered that? It is almost like, I give this example, you go to a tea shop and you say, how much is the tea cost? It's like $9, 9 rupees, and then you say like, take 10 rupees, give me 1 rupees back. But if somebody comes and tell me that tea is 8.9999999999999 rupees, and you take 10 rupees and say like, give me 1.0000000, can you do that business? Not possible. So it is exactly like that. Suddenly we are dealing with order one number and suddenly say no, this number has to be this. Then somebody says, okay, who cares? Just choose a number, erase 2, 3 zeros, but if you erase 2 zeros, you will be erased. Because if you erase 2 zeros, then cosmological constant will be higher to 2 orders magnitude, and it will take over the the gravity much earlier, and no galaxy can form. So you need that tiny number. And I know Institute of Advanced Study, there is a physicist called Nima Arkani Hamed, a great physicist. He gave a talk at ICTS. He said, this is such a big problem. So every day on my bed, while going to bed, I think about this problem and I don't get any solution, so I fall asleep. Okay, so that's the way, because there is no solution, that's where it comes from. There is one solution that I'll show you now, but many people does not believe it. It's called anthropic principle. It means some physicists say you should not ask this question. Why? Because if the value would be different, then there will be nobody to ask the question. As you are asking the questions, that means the value has been right. Are you confused? So that is okay. Okay, that is the called anthropic principle. Many top physicists are believing that you should not you should know what you should ask universe and what you should not ask universe. Okay, and according to that, universe will give you back the answer. Okay, now, so this is the status of dark energy. Nobody knows what the fundamental nature is, but it is all pervading energy with a negative pressure. Vacuum 0-point energy has is a possible candidate, but it has a huge mismatch. And then the fate of the universe basically is determined by the value and the nature of the dark energy. Okay, so now I'll move to very quickly to the DESI part. How much time do I have? 5 minutes. Okay. So now this is the video. What will happen to the universe if DESI result is wrong or DESI did not give a clue that dark energy is decaying?
The Big Bang giving rise to one time. And instead of
So there are many Big Bang happens. You cannot have just only one Big Bang. Each Big Bang in one universe, and it is called multiverse. Each of these universe has a specific value of lambda or dark energy. We happen to be in this universe where life can be possible. So now what will happen to the universe? Because cosmological constant will only drive things away faster and faster. At some point, other than our own galaxy, everything else will be moving faster than the speed of light and we cannot see them. So if dark energy is cosmological constant, if after 4 billion or 5 billion years later some planet has an astronomer, they will look and they will not get any other even galaxy to see because everything has been stretched away by the dark energy. And once they see our paper that we have found billions of galaxies, they will say what these people has done. So they will perhaps not believe us. Because for them the reality is the only one galaxy. But now, I'll move a little bit faster as I don't have that much time. But once you have Big Bang, you all know about the cosmic microwave background, where the universe was very hot plasma, and at some point, the atom forms and the electron and the nucleus binds because photon energy is no more higher to ionize it, and that is called fossil radiation. And Planck's satellite has detected it, this from here. And this is related to the BAO result, which I'll be discussing today. So what happens, before CMB, the photon and the visible matters, they were coupled. It is like an engine is pulling a train. So photon is the engine because it has pressure, and just like in the waves, sound wave has pressure. That's why it does that. So what was happening in the early universe, this is the density of matter, but it is coupled with photon. So what happens? The gravity will come, then bring them closer, but at some point photon pressure will say stop because it is too much. Then photon pressure will win over gravity. So then this part will start going down, and then there will be just like a ripple which will travel, that called the sound wave of early universe plasma. Visible matter coupled to photon. Now what happens? They were pulling and this ring was going away. But the moment photon decouples from matter, as I showed in the CMB, the engine will be decoupled from the train. So photon will say goodbye to the baryons, and the baryons or the visible matter will stop here, and the photon will start traveling freely, and that's what we see them. Now, this little extra height or extra density zone, we can see them today because those around that ring, there will be more galaxy because this has more matter. So that's what exactly happens. And this length scale is called 500 million light year, we know from calculation, or 150 megaparsec. This length scale is fixed. It is called Baryonic Acoustic Ring. This is what you should see. This is artist depiction. And this ring, actually it is a sphere. You have extra galaxy cluster when you see in the telescope. And that's what DESI has exactly done it. Now, how do we measure the acceleration of the universe from there? See, first they are formed. Now that length scale is fixed because nobody is pulling that engine anymore, pulling that train. But universe is expanding. So it will become bigger and bigger and bigger. What DESI does with a very sophisticated instrument, measure millions of galaxies to a very early universe, and they cannot do that with supernova. So they have another technique. And then they plot this different redshift, this ring size. And then depending on the ring size, you know that how much universe has expanded from here to here, because that is what only stretching the ring. And they found if it was a dark energy, the ring size would have been little bit bigger. but they are getting a smaller ring size. That means dark energy is decaying. That means if it decays, it cannot be vacuum energy. Vacuum energy is a constant thing. So it is something else, like the Higgs particle or the God particle, so-called. It is also a scalar field. So similar thing has to come into the play if this result is right. So this is the idea. The video, then I'll show the result. So this is the early universe. Because the photon says goodbye, and a little extra effect was there on around the ring. And then it become bigger, bigger, bigger. And this scale we measure the radius of the ring, and that gets a peak. So now this is the instrument DESI in Arizona Tucson, very sophisticated instrument, and this small video will tell you. Then to its 6 lenses that ensure resonance sky. So this is a spectrometer where it has 5,000 robotic element which detects the light from one direction. So you will see. First reflects off of the telescope's 15 times, then into its 6 large lenses that ensure designated wide, highly focused view of the sky. It focuses then here at the focal plane, and then the sensors are here. These lenses can be adjusted with preserve alignment lenses. After passing through the galaxy's light reaches fiber optics. The top telescope. So this is where the focal plane, there are 5,000 robotic fiber optic cable, and they are pre-programmed. And that's why it is called 5,000 eyes. From one direction, it can give you 5,000 spectra of galaxies. I'll keep the technical part. I also don't work on the instrumentation. So this is the actual data. They show it in the planetarium by the director of the DESI from Berkeley. So you are flying through the DESI data. This is where they have covered for the first release. This part they will be doing for the second release 2 years from now. It is also in the YouTube. It's called Flying Through the DESI Data. And you see there basically position versus velocity, that graph they are getting.
Oh, really?
So now these are the peaks at different redshift, different epoch of time. And from there, this line, this little deviation with respect to cosmological constant is the straight line 1. It's a 2.5 sigma mismatch. That means they are saying it statistically it means 2.5 sigma means 1 chance in 400 that you can be wrong, in DESI can be wrong. Yeah. So now the next data release will basically tell us the sigma will go to 5 sigma. That means 1 chance in million DESI can be wrong. That is called sometimes that discovery. Okay, so that will need more data, and actually data is taken. They have already gone through 3 years and they are now processing the data. It will take 1 or 2 years, one and a half year to get the next result. There you may see that this will come much, or you may see it merges with cosmological constant. Okay, so now this is the plot-wise mismatch. Here your dark energy as cosmological constant. That video, universe will expand and we'll all end up in emptiness. But this is where if it comes here, that means dark energy is decaying, dark energy is losing its strength. And then there is a chance that instead of going here, that is the cosmological constant, which Einstein's first put in the wrong side, then discovery put it on the right side, and then DESI may again take it away. So it's very interesting, the history of cosmological constant. Okay, and this might be the case, but we cannot tell here that this is the case. This needs more study, that we might end up in a big crunch or a cyclic universe, but at least DESI is first time ever in the 20 years giving a doubt on the cosmological constant. That's amazing with this technological advancement. that our fate of the universe is different and this is very interesting and we still don't know what it is. And then it means it's decaying little bit, but where it goes we don't know, but it is not cosmological constant. So, thank you so much. Time we have? One question, or later we'll take
Thanks, Subinoy. I think when I was doing my PhD is when I think Rice Perlmutter result came out, and then we thought, okay, now we're told we know what's happening, so it's good to know that we don't know what's happening yet again. We'll just take one question now, we'll come back to them after the second talk. Any quick basic question we have, we can take it, else we'll move on to the second talk and come back to Subinoy later. Okay, then let's thank Subinoy once again. And our second billing here is Sanved Kolekar, who's also a faculty here at the Indian Institute of Astrophysics. He did his PhD in IUCAA with T. Padmanabhan, whom you might have heard of. And his thesis was on gravitational dynamics and thermodynamics of horizons. After his PhD, he was in various places like the Kavli Institute in China, Nottingham in the UK, in CNRS in Marseille, and later in DEA in Mumbai, after which he joined our institute here. His area of research is gravitation, black hole physics, including black hole shadows, which we'll talk about today, quasi-normal modes, quantum field effects in curved spacetimes, and Hawking radiation. Today he's going to talk about the EHT results announced earlier this year of the polarization image of Sagittarius A star. So I'll tell you when 5 minutes are left. Sorry.
Yeah. So thanks Neeraj for that introduction, and also thanks for arranging this talk. Okay, so I'm assuming that you have at least seen this picture in the newspaper when the discovery basically came about. Okay, so this is supposed to be the picture of the supermassive black hole at the center of our Milky Way galaxy, and the first picture was released earlier. Now this is the upgraded version with basically those lines which you see. Okay, so there is a common confusion that people think that it's basically showing the magnetic field lines along the supermassive black hole. Okay, but it is not. It's basically showing you the polarization lines, which basically I'll describe what they are and how they essentially determine it. Okay, we'll also look at the feature which you see in this picture, that there is basically a dark region in the center, and then there is a sort of a ring thing with variable intensities at different parts. So why they arise, why do we have such a picture, whether this is a general feature of just the black hole at our center of our galaxy, or other supermassive black holes also have such features. Okay, so it is deeply connected to the theory of gravity as proposed by Einstein. Okay, and of course this picture is taken by the Event Horizon Telescope. So it's not a single telescope. They basically borrow the radio telescopes all over the world. Okay, they have proposal and they basically observe the same object for, let's say, very long time, 7 to 8 hours continuously, and then they basically collect the data, sync the data, and from there they essentially generate the image. Okay, so all the images and videos which you see in this slide are not mine. I'm a theoretical physicist. I don't know how to draw diagrams. I only know how to write equations. So the credit goes to EHT and the other sources which I took from online by searching Google. Okay, and they are for educational purposes. So Neeraj tells me it is okay to take it. Okay, so a quick recap of what are black holes. I'm very sure all of you over here would already have an idea of what are black holes. So I'll just quickly go through them. So the key idea is again from Einstein's theory of general relativity, right? Matter curves the background and background tells matter how to move. That is the theory of general relativity. The equation which you basically see there is the Einstein field equation. Okay, so you have some massive body and it basically bends the space and time around it. Okay, so the space-time is not flat. That was the key idea, and the principle which basically lead to that idea is the principle of equivalence. So since we are a bit short in time, what I will do is I will only explain those concepts which will be needed to explain the image, and if we have time later I will basically come back to it. Okay, so essentially the idea is the following. So I need to explain this because I would need it to explain light bending. Okay, So think of this rubber sheet, okay? I'm sure all of you might have already known this example, so let me just quickly rehash it. So take a rubber sheet, and if you drop basically an object on it, you know that it bends, okay? And let's say if there is an ant who is walking on that rubber sheet, if in the absence of any mass, it will follow this path, which looks like a straight line. But because of the presence of the mass, the rubber sheet basically bends down. So now the path of the ant looks curved from the perspective through which we are looking, okay? So this is basically an analogy of what would happen if the space-time is curved, okay? So straight lines do not look straight, okay? They appear to be bent, and that is why how we describe that is the effect of gravity, okay? It's no longer a force, it essentially affects the background space-time curvature, and because the space-time is curved, objects which go around it look like they are actually going on a curved path, okay? And this also happens with light. That was the crucial input given by the theory of general relativity. This was not there in theory of Newton's gravity, okay? Fine, so just a caution that in this analogy, remember this is just an analogy, not to be taken thoroughly too much, because if you try to look at in the four-dimensional space-time, okay, the circular orbit of particles, they actually don't go around in circles. There is a time direction, so basically they look like spiral, okay? So in this analogy, remember that there is an external viewing point, okay, and then there is gravity present which actually bends it down, but that is not what truly happens, okay? In theory of general relativity, automatically the space-time would be curved as per that equations. Okay, so there is a particular formula for the bending of light, which was the first test of general relativity, okay? That was measured during this solar eclipse by Eddington, and the data there was not so good to actually conclude that GR is correct, but nevertheless he made a bet and said that whatever GR predicts, the bending of light is exactly the same. So his idea was the following, that you look at basically a star and you know the position, okay? During the solar eclipse, what happens when the star is exactly behind the sun, okay? The light is passing very close to the sun, so the curvature of the space-time near the region of the sun will bend the light ray, and the position will basically be a little bit different. There will be a change in the position. So we can figure out what is the change in the angle as predicted by the theory, and that number you could match, okay? And of course later people have done precise experiments, okay, to measure that number, and it is very consistent with the theory of general relativity, okay? Now black holes are basically solutions which are kind of extreme, okay? So they have an extreme effect of bending the space-time around it, such that it is believed that there is basically a tear in the space-time, okay? The curvature is a quantity which basically measures how much the space-time bends, okay? And a black hole is an object which basically introduces a tear in that space-time, okay, at the center, which is called as the singularity, okay? But there are other nice features, that there is an event horizon which basically follows the creation of a black hole, okay? The solution tells us that there is a certain radius. So suppose you have a spherically symmetric object, okay, and you compress the matter into a small radius, okay? What radius? The radius is given by this particular formula. So if you compress all the matter inside this particular radius, so in this formula, let's say if you take the mass of the sun, then the corresponding radius would be around 3 kilometers. So if you compress the sun less than 3 kilometers, then you would have an event horizon. And the event horizon is such a boundary which basically doesn't allow light to even escape from inside, okay? So what we say is basically gravity is so strong that the fastest particle in the universe, which is the light, okay, there is nothing which goes faster than the speed of light. At least that is what we believe based on our current theories, okay? So even the fastest particle cannot escape if it is inside this particular radius, okay? So that is why the name black hole, okay? And this is essentially the event horizon. But what I said is about for a spherically symmetric object, okay? But you can have spinning objects. So if there are spinning objects, this formula will change, because then the solution is a different solution. It's a curved solution. And we believe that all the black holes in our universe would already have some spin, because they are a result of the formation of some astrophysical objects, and angular momentum is already present. You cannot decay away all the angular momentum. So whenever a black hole forms out of some astrophysical objects which is spinning, okay, the resultant black hole will also have a spin. Then the formula changes, okay, but nevertheless you still have a event horizon. So the event horizon is a genuine feature of a black hole. Okay. Now, other than the spin, there is one more parameter which can basically describe a black hole, that is the charge. Okay, so a black hole can be described only by three parameters. Okay, there is one theorem called the no-hair theorem which says that whenever a black hole exists, it is only described by three parameters, which is the mass, the charge, and the spin, which is through this J, which is the angular momentum. Okay, so it doesn't remember how it formed. Okay, so it could have formed from different constituents of matter, but once the black hole is formed and the event horizon is created, it will be described, the geometry outside the black hole will be described only by three parameters. Of course, the functional form may be different, but only three parameters come. All the information about the constituents, it actually goes away. Okay. Yeah, a simple way to think about the event horizon is basically this escape velocity problem, that if you try to throw an object up, okay, and if it has to escape the gravity of the system, you need to give it a starting initial velocity. Okay, so the event horizon surface can be thought of a surface at which the escape velocity actually equals the velocity of light. Okay, so that's why nothing faster can exist, so nothing can escape. But actually that's a wrong misnomer, because when you think about escape velocity, something goes up and comes down. Okay, so in a black hole, it actually cannot escape the surface itself. Okay, but for calculation purposes, if you try out this simple example, try to calculate the escape velocity on the surface of a, let's say, a spherically symmetric body using normal Newtonian gravity equations, the Schwarzschild radius or the event horizon radius will come out automatically if you put the escape velocity to be the speed of light. Okay, so there are nice properties for the black hole, but I'll just describe whatever is required for this part. So we have a time dilation effect which says basically clocks run slower in a strong gravitational field. Then the effect converse to this is basically the gravitational redshift effect, which basically says that if you have photon moving through the gravitational field of the black hole, then the redshift changes. The energy of the photon essentially changes. Okay, it loses energy if it wants to come from a stronger gravitational field to a weaker gravitational field. Okay, a closer analogy is the analogy of the gravitational potential energy, which you have learned in your Newtonian dynamics, that if something has to come out from a gravitational potential, it must basically decrease its kinetic energy. But for a photon, it always moves at the speed of light, so it can only give up the energy through its frequency. Okay, the frequency of the energy of the photon is proportional to the frequency. So if it has to lose energy, it must decrease its frequency. Okay, so that is what we say, it redshifts. It goes to the lower end of the spectrum, and the opposite will happen if you throw a photon essentially inside. Then there are these tidal effects. Okay, if you throw some large body, okay, close to the, let's say to the black hole, then because of the difference in the value of, let's say, the corresponding g, the gravitational acceleration at different points, the body would be deformed. Okay, the head and the feet, they would basically be stretched. Okay, and the width will essentially be decreased. So if you want a good photograph, you go close to the black hole and you will look very slim and tall, and it will be a nice photograph. Okay, so this I have already mentioned. This is the no-hair theorem. Okay, there is another effect called the frame dragging effect. Okay, which I will describe briefly because it will be needed later. So what it tells you is that if you have a rotating body, because of the angular momentum of the rotating body, it basically drags the space-time in the same sense of direction of the rotation of the body. Okay, so imagine there is some space-time over here. So you can imagine some grid. Okay, the grid is supposed to represent some rulers, measure of distances. Okay, because the central body is spinning, what happens is it drags the outside space-time in the same sense of the direction of rotation. Okay, so you can see that the grid actually starts to deform. Okay, so this is essentially the frame dragging effect. What it means is if you leave a body at rest, okay, at least radially over here, okay, just balancing the radial pull of the black hole, it cannot stay still in the phi direction. Okay, because of the spin of the black hole, let's say in this direction, it will start to move in the same sense of the black hole. Okay, and black holes has different regions because of this effect called as the ergo region, where the dragging of the space-time is so strong that if you try to send a photon in the opposite direction, it cannot. It will be forced to rotate in the same direction as the sense of the black hole is rotating. Okay, that region is called as the ergo region. Okay, so we'll require this concept later. Another interesting effect, I'm sure all of you have already heard about this, is the Hawking radiation. That classically nothing can escape the event horizon of the black hole, but if you use GR in combination with quantum field theory near the horizon, then it is possible for some photons to basically be generated near the horizon. Okay, it has to again do with this uncertainty principle used near the horizon. Okay, you can violate the uncertainty principle. Let's say some pair of particles are created. It could happen that one of the particle could go in, so whatever is left out cannot actually recombine and go into the vacuum, so whatever is left outside comes as a photon. The curious result is it is basically a thermal type of radiation. It could have been some radiation, but the remarkable result is that it gives you a thermal bath. Okay, and the temperature is connected to the geometric properties of the space-time around it. So it is connected to the geometry of the event horizon, specifically the surface gravity. Okay, so this is still an outstanding puzzle about the Hawking radiation, that what would happen at the end of the life of the black hole if it continues to evaporate through this Hawking radiation, what would be left. Okay, and it doesn't go well with the no-hell theorem which I just mentioned earlier. So it leads to a paradox called as the information loss paradox, but perhaps that's a talk for another time. Okay, so how do black holes form? So we believe that there are astrophysical processes that at the end of the life of certain massive stars beyond a certain mass, at the end of the collapse, so generally there is a balancing going on between gravity and pressure. Pressure due to the photons and the material, hot material, which is created inside due to nuclear fission at the core of the stars, okay, which balances the gravity. But once that fuel essentially ends up, gravity wins over, everything collapses, okay, and you can have a compact body necessary to form a black hole. Okay, so yeah, so this limit was famously given by Chandrasekhar, okay, and then later it was improved using taking into account different quantum effects. Okay, so this is how we believe black holes are supposed to be formed. Okay, so what are the different types of black holes that are found in the universe? So of course we have the stellar mass black holes. Okay, then there are supermassive black holes. This we believe exist at the center of, let's say, galaxies, big galaxies, and they have, let's say, masses ranging from 10 power 6 to 10 power 9 solar masses, which is like million to billion times the solar masses. And then there could be intermediate black holes, which are, let's say, 1000 times. Okay, so each one has this curious questions of how essentially they are formed. Okay, fine. So now let's go to a supermassive black hole case, because we are supposed to talk about the shadow of a supermassive black hole which is sitting at the center of our galaxy. So essentially what we believe is the environment around this supermassive black holes at the center of our galaxy. So what we believe is there is this black hole, okay, it is spinning. Then in this environment there is basically an accretion disk. The accretion disk consists of basically plasma, very hot plasma, okay, which is emitting this radiation, and it is actually moving around. So where does this thing come about? It could be because the black hole is eating the neighborhood stars, and because of the tidal effect which I described earlier, it could basically destroy the stars and then basically swirl all the constituents of the star matter into a hot plasma. That is what is essentially rotating about. Okay, then it also seems to have a jet. Okay, along the spin direction, it somehow seems to emit ultra relativistic particles going around at the comparable at the speed of light. Okay, and these we basically see as jets. Okay, coming from above the disk of the galaxy and below the disk of the galaxy. So this is the general picture that we essentially have. Okay, yeah, so this is about the theoretical description. Now the question is, how do we know whether they really exist in our universe? Because by definition black holes are supposed to be black, right? You are not supposed to see, because any light, there is no light coming out of it. The only light which comes is the Hawking radiation, but the temperature corresponding to Hawking radiation is so small That is, it is in principle not in principle. Today's technology is not able to detect it. Okay, so we should be able to detect any other effect which the black hole gives. And that is precisely what they did. So the Nobel Prize in Physics 2020 was awarded to this group of people. The theoretical part, Roger Penrose received half of the prize. He basically predicted that at the end of the collapse of certain heavy objects, okay, a black hole will form, and at the center of the black hole, a singularity will always exist. That was the proof of his theorem. It's called as the singularity theorems, and it was such a strong proof that initially people thought that maybe the solutions only work for certain symmetries which were assumed, like spherical symmetry or axisymmetry. But in the real astrophysical situations, you could basically deviate away from such symmetries. So perhaps the corresponding objects which are created may not have a singularity at the center, but his theorem was so strong which said that in any case, if such a collapse happens, okay, then a singularity is unavoidable and the black hole will also form. The other half was for the observation, okay, and the observation was basically of the stars which are at the center of our Milky Way galaxy, okay. So these people, they basically observed the motion of stars at the center of our galaxy, and the observation was actually possible because of a technique called adaptive optics, which actually resulted in a clearer picture. So the left one is without the adaptive optics, the right one is with the adaptive optics, and it helped in actually upgrading the technology and making this observation. So I'll just show you what is the observation. Okay, so here you would see the year in which they observed the position of the stars. Okay, this star is supposed to denote where the center of the galaxy is supposed to be. Okay, and basically they recorded the position of the stars. Yeah. So you can see the year over here. So this picture is through an old data. It will stop after some time, but now people have continued to monitor the motions further, so they will plot the trajectories even further. Okay, so notice the star over here which is going close to this center, which we believe it is. Okay, and just look at the shape that it has created. So what do you think the shape is? Yeah, it looks like an ellipse, right? And we have this derivation from Newton's gravity, the Kepler's laws. Okay, one of the Kepler's laws basically says that the motion of planets around the center, the source, is supposed to be in a plane, and it represents an ellipse. Okay, so this also looks the same. Okay, so first point, we believe at least the Newtonian dynamics up to some order is still valid even at an object so far from us. Okay, we are exactly observing the Newtonian dynamical solution over here. Okay, so that solution, if we believe and if we use the third law basically relates the time period to essentially the distance. Okay, and in that formula the mass also appears along with the gravitational constant. Okay, so the ellipse, you can measure what is the semi-major axis, you can put it there. The time period through the observation, you know, it is around, let's say it takes around 16 years, I believe. Okay, yeah, so this star is the SO2 star and it has a time period of around 16 years. So you know the parameters through these measurements, okay, and you can compute what is the central mass of that system. So it gives you a number that it is basically 4 million solar masses. So that's a very heavy, massive object, okay. And if you look at the scale of the system, okay, in which this mass is supposed to be concentrated, it's a very tiny scale, okay. So the only other denser object that we know in the universe was basically this dense globular clusters. Okay, so they had the mass of around maybe 10 power 5 or something, the density corresponding. But this object would have a density, if you concentrate it in some particular sphere, it would have a density which is around 10 power 15 times more than that object. Okay, so it was concluded that this highly compact object is basically a black hole. I mean, black hole is the best candidate which could basically describe this. Okay, and for this they were essentially given the Nobel Prize. Okay, so the other proof actually came through the gravitational wave detection. Okay, so the Nobel Prize in 2017 was given to this set of people for for their efforts in preparing the detector, but what the detector detected was essentially gravitational waves. Okay, I'm sure you must have also heard about what are gravitational waves. These are nothing but ripples in the space-time, background space-time. So objects create the curvature, but if I shake the object in center, okay, it is going to change the curvature of the background space-time, okay, and there is a chance that this thing would be periodic, so which is true in GR. So if you go very far off from the source, okay, then the changes in the curvature due to the dynamical motion of the object at the center, it creates these waves, okay, and those are gravitational waves. So the 2015 event, which was the first event of merger of two black holes, was detected, okay, and it gave a particular signature which you essentially see here, okay, and that concludes that these two objects which are essentially colliding were basically black holes. Okay, so that was another. And by the way, this Nobel Prize was given before the 2020 Nobel Prize, so people believe this more than the other first discovery. Yeah. Okay, so now coming back to what we are observing. Okay, so this is the 2021 picture. Okay, or this is basically the M87 picture of 2019. Okay, so over here you see this particular shape of the ring and the shadow in between. Okay, so we'll try to now understand how it forms, believing that the object at the center is essentially a black hole. Okay, because we know that they exist. Okay, so what is the object first of all we are observing? Okay, let's just look at the size. Okay, so the scale associated with this particular object. So first of all, it is this many light years away from the Earth. Okay, so and the size of the object at such a long distance, it basically subtends an angular size in the sky, which is comparable to, let's say, if you put a donut on the moon. Okay, and from here, if you were to observe the donut, whatever the angular size is subtended there, that is the size that the supermassive black hole basically subtends in the sky. Okay, right, so let's just zoom in, let's just give a feel of how small that object is. Okay, so basically this is the center of the Sagittarius, so basically it's called a Sagittarius A star, the black hole sitting at the center. We are away 27,000 light years. Okay, if you zoom in, if this is the scale at 500 light years, you zoom into 10 light years, then to 70 light days. Okay, and then you still zoom into 3 minutes. Okay, so this distance is 27,000 light years, and the scale at which the object basically subtends in the sky, it is basically 3 minutes. So 3 minutes to 27,000 light years. So that is how the object is small. Okay, so obviously the resolution of the EHT telescope has to be that good to essentially resolve that image. Okay, okay, so let's go into the zoom into the galaxy center. You'll have a lot of dust in between. Other stars basically still zooming. Zooming into that 3 minute scale. Okay. Yeah. So if you want to compare it with some scales in our solar system, this is how big it would be. Okay, so you go around to the orbit of Mercury around the sun, and that would be the scale of the object that you are measuring. But now remember, what was the mass? Okay, here you have one sun, and mass of the supermassive black hole is 4 into 10 power 6 times the solar mass. So you have actually basically compressed those many number of suns into such a tiny distance. Okay, actually the black hole is sitting somewhere over here. This is the extent of the shadow which you are seeing, so it is even more compact. Okay, so how is this picture formed? So it has to do with this bending of light, which I essentially told you. So this was at the scale of the solar system, but do we observe the bending of light even at other scales? Yes. So if you go, let's say, to the clusters of galaxies, okay, you have some mass collection of different galaxies sitting at somewhere in between, and if you are looking at some source which is behind it, okay, then because of the bending of light, when you basically take a picture of this particular source, okay, you will see many images, because the light which is coming from this source is following different paths, and because of the bending of light due to this mass which is sitting at the center, not the center or this particular location, it is bending and reaching to it. So you would see multiple images of that object. Okay, so this is the same bending of light, okay, but at a very large scale which you are seeing. Okay, so will this help in explaining? To some sense, yes, but the bending of light near a black hole is very extreme. The bending of light which we saw before is only a slight bending, okay, which is given by some approximate formula. But light could be bent in such a strong way that it could actually move in circles around the black hole. So that is possible, okay. It is not possible for the other objects that we know, because what happens is the boundary of the other objects are much beyond the circular orbit possible for photons. Till now, the only astrophysical object that we believe to have observed is the black hole, which could have this rings around, okay, and that plays an important part in actually building that shadow or creating that shadow, okay. So let's see how. So because this circular basically ring exists, it's actually not a ring, it's basically a sphere. Because of the spherical symmetry, okay, in any plane this ring can exist. So you can imagine that it will create a photon sphere, okay, of a particular radius around the black hole, okay, and it has a particular value, and that value which you can see over here. So this is the essentially the radius, okay. Now this has a property that because of the space-time curvature, if you have any other light photon which is coming from outside, okay, and it crosses this photon sphere, okay, then it is bound to go and hit the event horizon. It actually cannot go out again, okay. This has to do with the solutions of the light trajectories in the black hole background, okay. This is what happens after you solve the corresponding null geodesics, which are supposed to be the straight line trajectories for light, okay. The property is, if any light ray crosses this sphere coming from outside, okay, then it is bound to essentially go into the event horizon, okay. So what it means is those light rays which are at this photon sphere or outside, only they can go back out again, okay. So that basically classifies two set of light rays. The light rays which come closest to this particular photon sphere radius and outside, they can again go back out, okay, based on the trajectory. And the other class of trajectories are, once they cross this particular ring, they have to go and fall into the event horizon, okay. And this is the thing which basically creates that image, okay. So whatever I have described, this is the essentially the thing. So these are all the set of trajectories which have crossed this photon sphere, and then they were forced to go into the event horizon. These are the set of trajectories which actually do not come closer than this photon sphere radius starting from outside. So they can actually, let's say, make one round and go back again, make two rounds and go back again, 3 rounds, n number of rounds, okay, and possibly escape back, okay. So this is the classification. So this already tells you that this is going to create an empty patch over here, because if you are looking from outside, you are only going to get those class of trajectories which have been able to escape back to infinity. You will not get these set of trajectories, correct, because they are already fallen into the event horizon. So for you, this region is going to look pitch black, because there is no light which can come to you from inside this part, okay, unless it starts from that region, but that is not the assumption, okay. So this is going to look dark, okay. So yeah, so this is what I described. Whatever light which is coming to you, it can basically make not a single round or 1 round, 2 round, many rounds, and then come back to you, okay. But now we have to talk about the shadow, okay. Now generally when one thinks of shadows, one basically draws this straight line diagrams, okay. That is how we have been used to draw diagrams of shadows in school, okay. But this will not be true for a black hole, because now straight lines don't exist in the black hole background. So we have to talk about the class of trajectories which I just described, okay, and that is what is going to create the image. Now we also have to talk about what is the source of light, okay. The black hole is not emitting the light, It is something else which is basically illuminating the black hole, okay, and that light is essentially coming to us. So what is the source? Now I told you supermassive black holes generally we believe lie in this environment. So there is a accretion disk, okay, so which is the source of light, okay, and that light is what actually comes to us. So over here, whatever light is emitted from this region, you classify it into two classes, okay. One which goes closer than that photon sphere, which will not come to us, which will fall into the event horizon. The other things which will come out, okay. So we will trace only those trajectories of light which basically can come out, okay, and then look how the image is formed, okay. So this is basically the picture how it would be. I'll also show you a nice graphic. So these are the rays which basically maybe only slightly bend, okay, and if you collect such a class of rays, okay, and then project it on basically your camera, this is how the picture will look like, okay. Then you have further those rays which actually, let's say, makes one particular circle around the black hole and then reach the screen. So if you collect those set of rays, you will again get a picture something like this. So the more number of circles it makes, it will be concentrated in a ring. The ring will become thinner and thinner. The larger number of revolutions, it will be very concentrated along that radius of the photon sphere. So it will make a projection of a ring which appears on the camera. Now if you collect all such rays and combine it, you will get a image which shows a dark patch in the middle, and then it will show you the ring structure, okay. So now you understand how the picture was formed. That ring structure is basically corresponding to the photon sphere which existed. The dark patch is because of those class of rays which cannot come out, okay. So essentially the dark patch is not the event horizon which you are observing. You are actually observing the boundary is the photon sphere which you are observing, okay. That's one of the crucial takeaways, okay. Now you must have also seen this picture in a famous movie, okay, in Interstellar, okay. So this is basically a black hole and you have the accretion disk around it. Now why do you get this particular thing on the upper side? Because the accretion disk will be in a plane around the black hole, right? So this is the accretion disk, okay. But why do you see this particular image over here? It is actually the backside of the accretion disk, okay. The accretion disk goes around it. So you are seeing the backside of the image because the light is actually bending on top of the black hole and then coming to it, okay. Similarly, this lower part of the thing, this is actually the lower side of the backside of the accretion disk, okay. So essentially when you take a picture of the black hole, okay, if black hole was a person, you could see the head of the black hole as well as the face at the same time, okay. This is what light bending does to the image of a black hole, okay. So okay, I'll skip this part. Yeah, the inclination also has some nice effect on the shape and intensity of the image of the black hole. So over here you can see the orientation and how it basically affects, okay. So by studying this picture you can know what is the inclination of the black hole, okay. And another effect the black hole has is due to the spin. Because of the spin of the black hole, there is essentially a squishing of this particular ring, okay. Because one side is moving towards you, the other is moving away from you. Because of the frame dragging effects, okay, which I mentioned, it basically squishes the ring. The ring is not symmetric for a spinning black hole. So if you try to measure the asymmetry in the ring, it tells you the information about how fast the black hole is moving. And studying this relation between the inclination and this will tell you what is the orientation. So this is what the EHT did, okay. Yeah, so this picture basically tells you just the comparison between the two pictures that were taken. One was the picture of the galaxy, the black hole at the center of our galaxy, and the other one was in the M87. This was the first picture which was released, and that black hole is actually very, very large, but it is also very, very far from us. It is around 55 million light years far from us. So the angular size, both of them subtend in the sky, is of comparable magnitude, comparable order, but it is actually much larger than this, okay. Yeah, this is basically the comparison numbers, okay. Then there are some issues due to variability, because Sagittarius A star is not a very active black hole. There is not much matter, so occasionally something actually falls into it. So it is a very low light picture that you are trying to take. So you have to take a long 7 to 8 hours exposure, and let's say the picture is very dark. So just imagine that there is dog running around, let's say in the background, and the picture is very dark and you are taking a very long exposure. Then what do you see the dog as? You will not see the dog as a dog. It will be basically a long exposure trail of the dog running around, right? So that is why the picture essentially gets blurred like this. And the blurriness in the Sagittarius A star is more than the M87 because M87 being very large, it takes a long time for the light to actually make one round around the black hole. So the scale of variability is different for Sagittarius A star. For Sagittarius A star, it takes about 3 minutes. Okay, so that is in hours. Okay, so because of the variability scale, the M87 picture is relatively clearer than the Sagittarius A star. Okay, so this is about the variability. Okay, so how they basically figure out what are the parameters? So this is done by modeling. So you assume a lot of different models with different parameters. You get a particular simulated output, and then you match it with the observation, and whatever is the best fit model tells you is the central black hole. Okay, so these are just some of the samples. Okay, they basically took all the whole parameter range to figure out what is the best match, and this is the best fit parameters for the center. Okay, so the corresponding mass, okay, in millions, then the inclination, okay, and then what is the spin parameter. So it is telling you the corresponding numbers. Okay, now the latest image which was basically released, it has this wavy line patterns on the image. Okay, so what are they? They are essentially the polarized image of the same system. Okay, so you see this vectors or lines given over here. So corresponding to that, this image is actually created. So you don't see this image directly. Okay, this image is actually created based on the information about the polarization. Okay, so essentially what is polarization? So let me just give you a brief recap. Okay, so you know light electromagnetic wave. Okay, it's a combination of basically electric and magnetic fields which go in union, and that's why the energy is propagated ahead. Okay, so let's say if the direction of propagation is something like this, it's a transverse wave. So the electric field and the magnetic field, they essentially oscillate perpendicular to the direction of motion of the wave. Okay, so okay, this is again an animation of the same thing. So if you look over here, this corresponds to a linearized polarized wave. Okay, so what it tells you is the direction in which the electric vector will essentially oscillate. So the word linear actually tells you it's actually going in one particular line. Okay, so if this is the direction of Z is the direction of propagation of the light wave, then the electric field is oscillating in the Y direction and the B is in the Z direction. So this is basically a linearly polarized wave. We can also have circularly polarized wave where the electric vector actually rotates as the wave moves forward. So it can go in a cyclic way or a clockwise way or an anti-clockwise way. Okay, so you can classify electromagnetic light as such. Now a normal torch, when it emits light, it's a mixture of all possible directions of polarization. So we call it as unpolarized. Okay, it's the sum of all possible polarizations. Then you can have filters. Okay, you can place filters in in front of source of light and block certain polarizations and only allow certain polarizations to go through. So I'm sure you must have used this Polaroid glasses, through which if you look at certain things, then it will only allow a particular polarized light to go. Okay, I believe even our mobile screens, they emit this polarized light. If you try it with some Polaroid goggles, then you will see that the light emitted from our mobile screens, that is also along a particular direction. Okay, so this is what they essentially measured in the black hole image. Now instead of just looking at the intensity in a particular wavelength, they also looked at what is the direction of polarization of the light which is coming from the black hole image. Okay, but now if you see such a picture, it should tell you what you are trying to understand about the source. Okay, what is the reason behind this polarization? So normally polarization, let's say on the earth surfaces, can happen when there is basically scattering or reflection of light from a surface. For example, if you try to look from Polaroid glasses, the light reflected, let's say from the surface of a lake or ocean, you will see that it will have a certain type of polarization depending on the angle and how the surface is. Okay, the other way is when the light is emitted when charged particles basically move in a magnetic field. Okay, you're familiar with the Lorentz force, so you know velocity which is perpendicular to the direction of the magnetic field, that will give rise to a Lorentz force, and accelerating charge, they basically emit radiation. Okay, so this synchrotron radiation, whenever a charged particle is moving in a magnetic field, it will emit this polarized light. Okay, and it is generally perpendicular to the direction of the magnetic field. Okay, so this is what is believed is going to happen near the black hole. If you were to see polarized light, okay, the general belief is it would be due to the synchrotron radiation. Okay, so there must exist, first of all, magnetic fields near the black hole, otherwise you can't get synchrotron radiation. Okay, but that is possible because I told you the environment of the black hole is very hot, so it is filled with plasma, okay, which can generate that magnetic field, and you can have charged particles which are moving in the vicinity of the magnetic field. So this is basically a simulation of the plasma, okay, around the black hole, and this is the jet which I was talking about. And over here, this simulation shows you how the magnetic field lines actually behave. So these white lines which you see as fluctuating and actually moving around, these are supposedly the magnetic field lines around the black hole. Okay. So now if you have, let's say, charged particles which are moving around because of the synchrotron radiation, you could have basically polarized radiation coming out of it. So if you measure the radiation, you can try to estimate what is the magnetic field near the black hole. And the magnetic field is very important because actually that is the one which gives rise to these jets which come out from the spin axis along the black holes. Okay. So different orientations, suppose if you have a magnetic field which is, let's say, circular, okay, then it will give you polarization vectors which are something like this. So this is the direction in which the electric field will oscillate. Okay, they will be radially outward. If you have a magnetic field which is essentially radially outward, then it would lead to polarization which is essentially toroidal. Okay, and different configurations. So this is basically an image which tells you how the picture will look on a screen. Okay, so assume for a moment this is the black hole, and let's say you have magnetic fields which are these purple lines which are going around the black hole. So this radiation which actually comes from it will be polarized, and it will show a particular pattern on the screen depending on the what is the magnetic field configuration over there. So for circular magnetic field, you are going to get radial polarization lines. Okay, if you change the magnetic field configurations, okay, if you basically twist them a little bit, okay, then it will give you a polarization pattern which is corresponding to it because it is perpendicular to the direction of the magnetic field. Okay, so it will give you a polarization pattern which is something like this. So by looking at the polarization pattern, you can try to reconstruct how the magnetic field actually looks like. Okay, now what happens with the magnetic field is due to the frame dragging effect. Okay, because of this frame dragging, initially if you even had a simple magnetic field line, okay, because of the rotation of the black hole, because of this frame dragging effect, it's dragging the whole space-time around it. Even this magnetic field lines will actually tend up wounding itself, okay, or twisting itself, okay, because of which it will become a very complex structure. Okay, so the EHT collaboration basically put all the theory about the MHD, okay, GR-MHD, which is general relativity and magnetohydrodynamics. They essentially had a model for how the plasma will be. Based on that, they determined what the magnetic field lines would be. Based on that, they determined the synchrotron radiation and the polarization. Then they had different ways of distributing the plasma and hence the magnetic field. And then they again came up with different images possible. Then they matched it with observation, okay, and the best fit was essentially determined. Now, one important thing which is to be mentioned is the what is the relevance of this polarized imaging. So both this picture, at the outside it looks the same, okay, but they have different distributions of plasma. But yet, if you look only at the intensity versus position diagram, they look the same, okay, and this is the instantaneous picture what you see. Now in EHT, you have the long exposure picture, okay, so what you see is the averaged image. So it will even look closer. So you are not able to distinguish which configuration it is, okay, if you ignore the polarization information. But once you put in the polarization information, it tells you that both the configuration is going to give you a different set of polarization. So essentially that information helps you to distinguish what is the basic configuration of plasma that you are supposed to start with. Okay, it helps you distinguish. Now you have actually more information. Okay, so this is the linear polarization, but then you can also have circular polarization. You can also observe the circular polarization. So this is the picture, this is the contours for the circular polarization. Okay, the red one might be, yeah, this is anti-clockwise, the blue is basically clockwise polarization. So if you observe this, you will know information about the magnetic field which is going into the plane or coming out of the plane. Okay, so it helps with basically modeling this. Okay, so I think maybe I'll just stop here because all the important part is covered. The rest can be maybe discussed later. Okay, so one common feature I'll just say is that the polarized picture of the M87 galaxy and the polarized picture of the Sagittarius A star, the Milky Way supermassive black hole picture, that picture, if you plot the polarized this pic, then it looks very same. Okay, so it again tells you that whatever we believed is the environment of the supermassive black holes, the basic structure, that is still the same, because even though the scales are different, okay, the underlying physics about the plasma and the magnetic field, it is still the same. Okay, so that helps us in basically believing in our theories that whatever physics we are essentially applying at both the different scales, they are still the same. Okay, so that was, I think, the last comment. Neeraj, sorry for overshooting.
Let's thank Sanved. I think compressing either the universe or a black hole into half an hour is not easy,
Yeah.
so I think that's all right. Maybe Sanved will also come here. So now we can take questions for both of them. We'll take a few questions from the audience here and then move on to the YouTube and Zoom people. Just raise your hand, I'll call on you. You can have questions for either of them, or if it's on general relativity, for both of them, that's fine too. Yeah. And here, Carl will then bring the mic to you.
Subinoy, you mentioned dark energy is like a fluid, right? And since it's accelerating, so is there by any chance the acceleration could be due to any perturbations, or the source of acceleration is it only because of the initial condition, or could there be any other reason for the acceleration?
Yeah, here you don't need any perturbation, just an homogeneous isotropic fluid pervading every point in the universe. If you put in Einstein's equation, you will get the universe accelerating automatically. So, but only thing you need is a negative pressure. So that's why we don't have such thing from known physics. So that's why it is called dark.
Also, one small doubt. So, dark energy, is it the expansion of space-time, or what exactly?
No, dark energy is not expansion of space-time. Space is expanding, but how fast it is expanding depends on what you put. It's very similar to black hole also. What you put, it tells how much space is curved. Here also, what you put tells how fast space expands. In fact, the expansion of space is actually kind of curvature only. INGR. Okay.
Thank you.
Yeah. Please put your hands up, then I'll call on you. Yeah. Both. Yeah, please speak into the mic because people online need to hear your question.
Both talk are nice. You mentioned the magnetic field around black hole. The origin of the magnetic field, what is the origin of that magnetic field?
It's because of the plasma. So charged particles are moving around in the accretion disk. So those are basically currents. So magnetic field will be generated.
My second question is because if black hole rotating, then around the space-time is rotating, then everything is dragging. But if you consider the field line, then you mention it also dragging. But it's not a particle, not a mass. Then how field line dragging around the?
Okay, so it is because of the currents. The plasma is also being frame drag, right? So it is frame drag in such a way that if you just look at the field lines, it will appear to be twisted because of the frame dragging. So ultimately it's the frame dragging which is affecting the plasma, which is giving rise to the magnetic field.
Due to frame dragging, the magnetic field created?
No.
No, the plasma itself
Yeah.
is
Plasma is
There is
creating the
drag.
magnetic
Right.
field. The plasma is frame drag, so indirectly the magnetic field is also frame drag.
And plasma is the collection of the charged particle, and then how it's created.
Because of the hot temperature over there, you have some disruption of, let's say, a star, which actually goes into that accretion disk. So you have this matter which is actually going around, and it's not freely falling, but it's falling in the potential. So it has to dissipate away that energy when it comes from a higher radius to a lower radius. So that is dissipated in terms of heat. I mean, that is one way. There are other processes also.
Yeah, and another question in formation of black hole, you mentioned only stellar E. If you consider that in early universe there is a huge perturbation, then it also become a primordial black holes maybe, that you did not mention. Do you believe that or not?
Yeah, so he is the expert on primordial black holes and their existence in cosmology.
He is the expert of modern black hole. I am the expert in the primordial black hole. Yeah, so many people believe that you cannot create the supermassive black hole from stellar collapse. That means it's hard to create. So many people think that even the larger number of primordial black hole may source into this huge, massive, supermassive black hole. There are theories on that, but till now we don't have a proof for primordial black hole yet. There are speculations, but there is no proof yet.
And yeah, the person. We'll come back to you with another question.
Here, Sanved here. So, the polarization can also be like caused due to the scattering of the photons with the particles in the accretion disk also. So, is it like in supermassive black holes only synchrotron radiation is the dominant one?
Yeah, it's the dominant one because you can have 100% polarization due to synchrotron radiation. Scattering won't give you that 100% polarization. There will be a certain fraction. So even this vectors which I showed you, it doesn't mean that the whole light which is coming from that area is 100% polarized. It's basically some fraction, and that fraction depends on actually the position, which is not given in this. Actually, it's given because if you look at the color plot, that blue to red, it's basically the fractional polarized light which is available over there. But if you want such a large fraction, then synchrotron radiation is the most dominant one, as you said.
Okay. And due to like the scattering also, that will be also affected by the frame breaking effect of it.
Whatever, yeah, so everything will be affected by frame dragging. There will be some polarization due to scattering, but I don't believe their simulations yet take into account the scattering basically effect. This is majority due to the synchrotron radiation.
Okay.
Sir, first of all, thank you so much for the talk. It was really interesting. And my question is twofold, and I think one part of it has already been discussed, but I'm not very sure because I'm not very familiar with the technical language. So my first question is to Dr. Kolekar. That is, you mentioned about the frame dragging. Now, I was trying to figure out why that happens. Do we assume that the black hole is the mass distribution is non-homogeneous, or I don't seem to find any reason for a homogeneous distribution to cause something like frame dragging? Could you shed some light on that? And my second question is to Dr. Subinoy. Regarding dark energy, could it be simply a mathematical or physical residue of a true solution to, let's say, an n-body problem of the entire universe, that maybe because of our lack of computation, we are not able to find those residual picture. We are not able to find it, or maybe because of certain approximations, we are not able to imagine such things to come naturally out of what we see today. So these are the two.
Okay. Yeah, you asked about homogeneous thing, right? Sorry, I forgot. I got interested in the second question. So you asked whether the distribution of matter is homogeneous.
Yes. So how can frame dragging come from a homogeneous?
So the solution of Kerr, it is basically a axisymmetric solution. So imagine, let's say, a spherically symmetric system which you are actually spinning, but then everything is not spherically symmetric, okay, because it will have some different effects. So see, when you talk about black holes, the distribution of matter doesn't exist, because everything, whatever matter has formed the black hole, it will go and sit at the singularity. Okay, so then there is no distribution of matter left. Whatever you are talking about is only through the geometry of the outside space-time curvature.
So
Okay.
could I say that if I am spinning, I cause a very feeble frame dragging?
That scale, okay, let's talk about the Earth. The Earth, because of its spinning, it will create a frame dragging effect. Yeah.
And that's been measured.
Yeah.
And that's been measured.
Yeah.
Okay. So, to answer your question, the in-body simulations are done with particles, okay? So, and that's where actually not dark energy, the dark matter goes into, and how the particle cluster in a galaxy, there people has tried to eliminate that. Maybe there is no dark matter, but maybe there is a modification in Newton's law that is called MOND, and people tried that and it explained the local structure of dark matter and the galaxy structure, and that is called MOND. But there has problem, because you need also dark matter during early universe, not just now, and that MOND cannot explain. So in the community MOND, the modified Newtonian dynamics, where there is no dark matter, 27% is not accepted that much. But for dark energy, it is not even clustering of particles. So it is just the expansion of the space, empty space, and you need a fluid which has these weird properties, and we don't know any such particle of our fundamental particle physics of so many particles and fluid which can create that property. So no, not a single one, except the vacuum energy, and that has also. So it is nothing to do with the in-body simulation, it's just the expansion of the space so fast, and that has to come. That is true from GR, general relativity, because you get the expansion of the space from the thing you put on the right side, and you need such weird unknown component, 70%.
The reason I had that question was when Dr. Kolekar started explaining about the usual rubber stretching example. Now, if you think about it in a very simplistic way, I was thinking that, let's say a rubber sheet, and I have another rubber sheet attached to the same rubber sheet. If I have a mass which I'm placing on the second rubber sheet, there's a sort of stretch I'm causing on the first one. Now, that is...
So that's true if you are in a local universe, but dark energy is happening everywhere. So you can explain that in a local expansion, maybe. But if it is happening from all the megaparsec, like billions of light years in all directions, then you don't, because for you, the answer you are giving, it is from a local dynamics. So but you cannot do it for everywhere, So that's why it is the property of the universe, not the individual things, but as a homogeneous universe, background. Okay, so
Yes.
yeah.
Let's take a few questions online and come back to the audience. So I'll try and club a few. First for Subinoy. One is a very basic question. Is a Hubble constant and cosmological constant same? What is the difference? So that you might want to just quickly address. And is there a remote possibility that dark energy will fragment the universe in the future? So those two you can take now, and then I'll give you.
So Hubble constant, the name is little bit confusing. Hubble constant is not a constant. Okay, it changes over time, but we tell it constant. Hubble constant, I don't know why. And cosmological constant is actually constant. The energy density, just because it's the energy of the nothing. So nothing energy, even if you stretch the universe, still it remains nothing. So its energy remains the same, energy density. So that's why cosmological constants are totally different. It is the energy, and Hubble constant is the rate of expansion of the space. Okay, but they are related. If you put cosmological constant, the rate of expansion become more. So they are related.
Yeah,
and the universe don't fragment, because for fragment you need asymmetry. But dark energy is like a very homogeneous thing. So homogeneous thing to fragment is hard. But yeah.
There's another question for you, I think relates to the expansion, the common question you get, which is that if you are talking big crunch after you put the brake on, then will the collapse be faster than the speed of light, and how will that happen?
So there has been model of big crunch, where the collapse is much faster than the speed of light. But for that, as I showed in the last plot, the dark energy has to be very extreme, and we don't have any such clue yet. But it is a possibility, because if it deviates from cosmological constant, whether it goes into big crunch and when the atoms also disrupt, so that we don't know. Because if the expansion rate becomes so high, then it can even tear apart the electron and the nucleus at some point. Okay, so but it's speculation, we don't know. But what DESI is showing first time, that it is a tiny deviation from lambda cosmological, and if it is a tiny, theoretical side is a huge, because you cannot, cosmological constant is really constant, you cannot even deviate little bit, so that means you have to go to completely different theoretical modeling. It is not that I'm changing the value of cosmological constant little bit, no. Constant means constant, is vacuum energy. So if you are getting a time varying thing decaying, that means it's something completely different, which may be a Higgs-like particle or another thing, which we don't know.
Thanks. A bunch of questions for Sanved from online. On Zoom, Shailaja asks, is there a way to isolate that part of the ring which has not undergone any gravitational bending? Do you want to take that?
Okay. So the photon sphere is basically the extreme bending of light near the black hole. So if you want let's say a photon to move on that photon sphere, it has to continuously be affected by the strong space-time curvature. So yeah, so the full ring is basically under the influence of strong bending of light.
Okay. The bunch of questions about exactly where the magnetic field comes from, which I think you answered already, so I'll skip that. And then the questions about so in a black hole, the plasma around the black hole, you said electrons move, I think, near the speed of light. I think the question I misunderstood that being at the speed of light, so there's a question, you might want to clarify that.
Yeah,
very
so they
quickly,
move
and then
near to the speed of light, so that is in the jets which come out from near the spin axis of the black hole, near the north and the south pole. So there basically whatever is ejected, it moves very close to the speed of light, so that is ultra relativistic. Yeah.
Yeah, and the last question is, does the magnetic field you showed have any effect on Earth? And I guess the answer is
Yeah, that's
no.
too far.
Yeah, it's too far, so it doesn't have any effect on Earth. We'll come back to the audience here. So other questions? Yes. You have the mic anyway.
Yeah. Nice talk, by the way. I have a question for Sanved sir. When we are talking about frame dragging or even expansion, so suppose my common sense says, okay, if something is stretching or something is twisting, there should be a limit after which it should be carried apart, right? So is space-time infinitely stretchable, or there is a limit for that? Like if you have a black hole and it's rotating, is there a limit up to which it can
In frame dragging, it is actually not stretching, because that's a stationary solution. So you can think of it like the following. So if you have, let's say, concentric rings which are rotating at different velocities, so just imagine that the ring inside is moving faster. So if you are putting some particle on top of that ring, let's say it is attached to that ring and it is forced to move at that particular velocity, angular velocity.
You want to use the board?
So that is how.
You want to use the board? Okay.
So that is how the frame dragging can be imagined. So it is not stretching. The stretching, what you are saying, is in the FRW metric, which is basically the expansion. So I think that part Subinoy can clarify.
So yeah, there is no limit to stretching, but when we see that there is a singularity, like 1/0 term comes, that means we say that the space-time is not defined anymore. So I think in the black hole singularity you get that, and also in the Big Bang singularity you also get the same thing. So but you can stretch infinite, but infinite means, what is infinite? Means we get that term 1/0 kind of thing. That means you know that you cannot write it.
But even if when we are talking about the event horizon, if you are like, we are considering the object which is stretching the space infinitely, right? But if we don't go to singularity at the event horizon, it is stretching the space, right? It's twisting the space. So is there any limit for that?
So the curvature is very well defined at the event horizon. There nothing goes back. So the place where the curvature actually becomes ill-defined is near the singularities. Okay, so in the spherically symmetric black hole, Schwarzschild black hole, the singularity is a point singularity. Okay, the center r equal to 0. But interestingly, for a rotating black hole curve, the singularity is not a point, it's actually a ring. The shape of a ring. Yeah, so only there the description about what the space-time is breaks down, because you don't want physical quantities to go to infinity. But near the event horizon, there is no problem. So, because let's say if you are in a rocket and you are crossing the event horizon, and if you don't look out, okay, you will not even know that you have crossed the event horizon because of the equivalence principle.
Yeah.
Hi, so my question is for Dr. Subinoy about the recent DESI results. You mentioned that if that lambda CDM is rejected by 2.5 sigma, that you need some kind of scalar field theory to explain what is going on. So could you elaborate a little bit on what kind of scalar field theories you think could solve that?
Yeah, so we know that scalar field exists in the universe, like Higgs is a scalar field, but it has to be a different scalar field, like inflation. You know, in the beginning, that rapid expansion, that is also a dark energy, you can say, like Matrix 1, Matrix 2 reloaded, 2 movies. So inflation is dark energy 1 and dark energy right now is dark energy 2 reloaded. Inflation time, people have already used scalar field models, and if this is true, then you need another. So maybe universe has a mechanism to create this acceleration time to time, because inflation started and it stopped. Maybe this one also, dark energy, started 4 billion years back and it will stop. So maybe it is pointing out to a hidden mechanism of the universe which it is using earlier and now also after 14 billion years. So that's, people are thinking it that way. But I will not go into the details of the scalar field, it will be then going above the thing. We can discuss later. Yeah.
Thank you.
Yeah.
Sir, I had a question. You had earlier mentioned regarding the intensity variations in image of the black hole. So could you just explain regarding why the intensity is there?
Okay. So one of the reasons is because of the Doppler effect. So accretion disk is actually going around the black hole. So the part which is going away will be basically redshifted. So the intensity formula is also affected because of this Doppler beaming effect which happens. So the other side is actually coming towards you, so that will give a higher intensity compared to the other part.
Yeah. Wait for a mic, please.
Hello.
Another mic is coming.
Hello. Yeah, for dark matter we know there is a attempt to consider as a particle, weak particle, neutrino particle, so on. But dark energy, this type of particle consideration going on, or
No, there is no such particle with
then
negative energy, negative pressure.
then for nature of the, we understand to nature of the dark energy, then how do we understand as not particle, then how?
It is an energy without a particle. It's a field. So, you know, field has a magnetic field, can be having energy, no? So like that scalar field is a field, but it's not a particle. Okay, because particle, then you need more particle to have a homogeneous fluid, right? And that fluid will never have negative pressure. Any particle you create, you will always have a positive pressure. You want to clamp them, they will. So it is a different thing. So your gaseous thing will not work, any. To dark matter it will work, but for dark energy is the pressure. Yeah.
Yeah.
Okay.
Next question.
I think no more.
Anything else? Anybody else? Any last questions on Zoom or YouTube? I don't see any. Last questions, comments? Yes, then we'll stop. Then the last question.
Yeah, I have read in a book that when a black hole is formed, there is a eruption of space-time curvature. So, is it true or not?
So when a black hole is formed, the singularity will be there as per Penrose's singularity theorems. So it is, so at the center of the black hole, if you are using still GR, then the curvature becomes infinity, so there will be a rupture in the space-time curvature. Yeah, it's true.
Okay, I think we'll stop here before the rains start. Thanks both Subinoy and Sanved for two remarkably singular talks. And though we stretched time a bit, I think that's fine. We are very happy with the fact that we got a chance to hear about two extreme examples of general theory. One is the entire universe, and the other is very close to a black hole. So when new such momentous discoveries or announcements are made in the field of astronomy, we hope to bring you more such public talks to try to explain what they are all about. So we continue the series as and when there are we'll see what the next big discovery or announcement is in the field of astronomy. Thanks everybody for coming here in person as well as being online on YouTube and Zoom. Thanks again to the speakers, and we